Thank you very much for the invitation. I will be talking about a work we published back in 2022 about the structure formation in an isotropic universe using the Eulerian perturbation theory. This work was made by Dr. Juan Pablo Beltrán, Dr. Jorge Noreña, Dr. Tiago Pereira, and Dr. Cesar Valenzuela, and myself. Okay, so despite the motivations to do this work was the idea that the universe is expanding, is accelerating, and we have doubts about the nature of dark energy. The most prominent model we have so far is the lambda CDM that states that the dark energy or the source of the accelerated expansion is a cosmological constant. Okay, this model is very successful in many observational data, but it has some problems. It has some tensions called H0 tension and sigma 8 tension or S8 tension. And the idea is that if the model is good, then we need only to test some assumptions see if those tests can contribute to alleviate these tensions, right? Our avenue was to test the cosmological principle that states that the universe is homogeneous and isotropic at sufficiently large scales. So to do so, we want to see what happens to this large scale structure formation in an isotropic universe. Okay, so our main objective is to test or to see what happens to the large scale structures formation in an homogeneous but an isotropic universe. And to do so, we use Bianchi I, the metric Bianchi I, and we do some assumptions to do the computations. The first one, the Newtonian approximation. So we do it because we are dealing with small peculiar velocities compared to the speed of light. Then we also do a small shear approximation because the observational data. Okay, the observational data states that the shear or the universe is quite isotropic, but then we want to test if maybe there is a degree of anisotropy. Okay. And the final assumption is that the fields, the perturbations are small, but the derivatives are big, are large. Okay. Okay. So, the Bianchi I metric can be written like this. The difference between the Bianchi I metric and the FRLW metric is the fact that gamma ij, the space, the metric to constant time hypersurface, superface, are time dependent. And then, because of that, we can define the geometric shear, which is given by the time derivatives of gamma. And we define also sigma squared like this because it will appear in the Einstein equations. Okay. To the background level, the equations can be written like this. We have a new term here, and we have this is the Friedmann equations. This is the traceless part of the spatial Einstein equation, and here we included pi ij, which is the anisotropic stress energy stress tensor, and we assume that it is sourced by dark energy. Okay. Then here we have the continuity equations to the background level. Here is for the matter. Here is for dark energy. You can see this is a new term. Okay. With all this, this is a part of the ingredients. This is the background construction, and then for perturbation, on top of that, we compute. We perturb the metric. Here we have the usual perturbations, but then here in the Bianchi I, we need to define the spatial perturbations like this. Okay, we use the Newtonian gauge to fix the gauge, and then in the Newtonian limit we can see here that that the perturbations, well, with the Newtonian limit we can check a typical size of the perturbation. So, for example, given CMB, or the data of CMB, we notice that phi is of order 10 to the minus 5. And this data is around k equal to AH. And so, because of that, we see that V is of order 10 to the minus 5, okay? But to small scales, meaning k larger than AH, then delta is of order 1, is big, and V is still small, still small, is of order 10 to the minus 3, and phi is also small, 10 to the minus 6, 5, okay? And then, checking these typical sizes, we made this table of this answer to the different perturbations and contributions to the equations. For example, the derivatives are big, of order epsilon minus epsilon to the power of minus 1/2. Epsilon is a small parameter. And then rho, delta, and theta, which is the divergence of the velocity, is of order 0. V is of order epsilon. Vi, this V is the scalar part of the velocity, Vi is the vector part. Vi is of order 1 epsilon to the 1/2. And then for the metric part, we have C and phi of order 1, omega I of order epsilon, of order epsilon to the 3/2, and tau ij of order 1, of order epsilon, okay? Then we computed the continuity equation here and the Euler equation here, two leading order in epsilon, and we found these two equations, okay? Leading order in epsilon and linear order in sigma, okay? And what we found is this. And these equations are very interesting. Here is the contribution of the shear, and here, and these equations are, in principle, to all orders in delta and theta perturbation. Okay. So you can see that if delta is of order 0, theta, which is the divergence of the velocity, is of order 0 in epsilon, also 0 in epsilon, and well, here is of order 1/2, but this is of order minus 1/2, epsilon to 1/2, epsilon to minus 1/2, and this is of epsilon 0. So all in all, this is of order epsilon to the power of 0, and here also, okay? Then, now that we found these equations, we want to solve them first to linear order and then to nonlinear order. And to linear order, we take out all the nonlinear terms, for example, this one and this one, or this one. And what we found is this equation, okay? And when we solve it, we solve in a typical way, and we found these kind of solutions, okay? You can see this D plus is the growing modes of the isotropic universe, and Qij is a quadrupolar contribution given by this. Okay, you can see the shear is the source of these quadrupolar solutions, and this dot here represents a derivative with respect to the scale factor, okay? And what we found is here we can see a plot about the difference between the isotropic, the ratio of the isotropic solutions and the anisotropic solutions for different values of pi ij, okay? I mentioned before that pi ij is the source of the shear, and then if we have a small pi ij, then we have a small source, a small shear, okay? Then we compute it to second order, and to second order, we keep this alpha and beta, which are integrals, and these integrals have a kernel, which is called alpha, and depend on the linear solutions, okay? And to solve these equations, what we did is we separated the isotropic part with the anisotropic contribution, in this case. For example, here, this d plus a times 1 will be the isotropic solution, and chi ij d plus times chi ij, the qij, sorry, will be the anisotropic contribution. And given that, then we computed the corrections, the anisotropic corrections, okay? And what we found is something like this, which is this, with this kernel being a complicated function of the shear, the time, and the momenta, and the kernels here. We notice here that this kernel is, well, is very, very big, and can well contribute to the power spectrum, the 2-point and the 3-point power spectrum. Because of time, I cannot show you our computations, but what I can say in this, here, well, maybe let me conclude. What I can conclude here or summarize here is that in this work, or in part of this work, we computed the Euler and continuity equations to the matter perturbation in an isotropic background, to a linear order in the anisotropy, and using these approximations mentioned before, the Newtonian approximation and the small field big derivative approximation, right? We solve the equations to linear order and to non-linear order and see how can it affect possibly can affect the power spectrum and the bispectrum. And we show that small deviations from isotropy can leave a signature on the matter power spectrum. Maybe what I didn't show, but it is a consequence of observations, is that these contributions can be obscured in the sense that the observational data is taken in redshift space. And redshift space has redshift space distortions, which contains quadruple contributions. So maybe the contributions of the anisotropy in the background can be enmascarated by these redshift space distortions. So our next work, the following work I want to say is that we are going to present we are going to study these redshift space distortions in an isotropic background, okay? And that's it for me. Thank you very much.